our focus area, including the thermal analysis, which used to determine the changes in dimensions, mass, phase transitions, enthalpies as a function of temperature. Also, we have the thermophysical property testing, which used to determination for the thermal conductivity, thermal expansion coefficient, and specific heat. Another part is adiabatic calorimetry, which used to analysis for the like degradation and reaction processes with regard to the temperature, dissipated heat, and pressure curve. Also, we provide services on the contracted works, seminars, testings, trainings, and meetings, and like webinars like this. Okay, so in the Nature America, we focus on the thermal analysis, thermal physics analysis, and as we all know, thermal analysis is super important for polymers. Here is show you a brief workflow in polymer industry. So it depends on what kind of properties you're going to explore. We can provide different methods to do for the job. Such as in the through the customer delivery to the quality control to storage step and the drying, feeding, and the process, and to the final product. And you can see we can provide all kinds of methods, including the TG, DSC, DMA, and LFA. So especially in this talk, we're going to focus on the TG-FTIR coupling, so you can see which have already been used broadly in the steps like quality control, the drying, feeding, and the final product characterization. Okay, so in this part 1 talk, I will give an introduction on the thermogravimetric analysis. First, talk about the basic principles of TGA and introduce our instrument features from NATCH. Then I will give a brief introduction on the TGA coupling with the evolved gate analysis, such as FTIR, GCMS, MS. Then I will turn over to Sergey for the detail in the TG-FTIR area. So as a standard definition for the thermogravimetric analysis is which is a technique to use to measure the mass of a material as a function of temperature or time when this material is subject to a controlled temperature program in a controlled atmosphere. That means in a controlled heating rate or cooling rate, then in either inert atmosphere or in air. And so a typical setup will be include a sample on the top of a balance, then use a furnace to do this controlled heat treatment. And here shows characteristic properties and the values for TGA. You can see from a typical TGA curve, you can get the mass change. And from the mass change DTG curve, you can get mass change rate, which is a derivation of the TG curve. And those DTG peaks, which show the characteristic temperatures for these mass loss depths, so which can help to get more accurate temperature on those mass loss. Also, the onset temperature in the TG curve can show you some information on the thermal stability. So TGA has been a very mature analytical tool which have been used in broad areas, including the mass change, decomposition temperature study, thermal stability study, decomposition analysis, and also in the advanced material analysis for the decomposition kinetics, rate controlled mass loss, density change. So next I will talk about the comparison for the different design principles on the thermal balances. Now in the market, there are majorly three types of design: the hand-down thermal balance, horizontal thermal balance, and also the top-loading thermal balance. So you can see from the scheme here to show you either the hand-down thermal balance and the horizontal design, they have their disadvantages. The major disadvantage would be, once risky to load the samples. So hand-down wire or the horizontal beam can be easily got bent or, crushed. And also, since this direction, to load the sample, the evolved gas, it comes from your sample, can condense on the balance arms or in the, contaminate the balance. So it's you will have not very good baseline, and also the drifting curves. Also, this will end in the large dead volume, which is not ideal for the evolved gas coupling later, because you need to flow the high gas rate to remove those evolved gas. And on the contrast, you can see top-loading thermal balance will be ideally suited for all these applications, because it not only provide a very easy operation and sample loading, but also it will allow the gases flow naturally in the upward direction. So that will easily to remove this from your away from the balance, and also you can directly couple those evolved gas analysis to on the top of the TGA. That will give you a small dead volume and a small gas flow rate, which are very ideal for the EGA analysis. And NACH instrument, the TG-FTIR, use this top-loading design. So here is a scheme picture to show the NACH TG-FTIR label. On the top, you can see the cover support. Then in the middle is a sample carrier, which it can be easily removed and changed by the user, not need the service guy. And also this, at the end of the sample carrier, we have automatic lifting devices, which can automatically disattach to the balance when the furnace is open. So that will make the sample loading is always risk-free. If you just by accident press the sample harder when you load them, but it's not going to hurt the balance because it's already be automatic attached. And the TG of NACH, they use a water jacket for the cooling, so make the cooling faster. Here show you the TG-FTIR label, some key features. As I mentioned before, we use a vertical top loading design for easy sample handling, and also provide natural gas flow upward. And also we have a wide temperature range, vary from 10 degrees to 1100. We also use a corrosion-resistant ceramic micro furnace, which have a long lifetime and faster measurements, can as fast as to 200K per minute in heating rate. Also, we use a CDTA for temperature calibration and caloric effects. So that kind of can provide you some similar DSC data through the calculated DTA. So that's pretty handy. If you don't have a DSC with you, this can also do some of the DSC's work. Also, we provide B-flat, which is automatic baseline correction, which will automatically consider the buoyancy effect and the drifting effect. So if you don't have time to run baseline, you can use a B-flat, which is already be stored in the software. Use that as a baseline to save you time. Some other features we include in the vacuum tight for the measurement, or we can go pretty good as low as 0.01 millibar vacuum, and it also be controlled through a auto vac for for automatic evacuation and the refilling of the gas. And we also have some other optional features, such as super res can provide a better control on the heating rate to give you better separation of overlapped peaks in the decomposition steps. And this TG Libero can attach to an auto-sampler for up to 64 different crucibles. Also, as I mentioned before, this top-loading design and other features make the TG Libero is very good candidate to coupling with other evolved gas analysis methods like FTIR, MS, GCMS. And in our recent released software, we have this new feature called automatic data evaluation, so which can automatically evaluate the mass change in the mass loss steps and also those like the residual mass. So just by one click, you got all the analysis results appeared automatically on the screen. So that will save time, and also that will ensure accuracy and consistency in the data evaluation. So to get more from the TG tool, we couple the TG Libero to the evolved gas analysis to get more identification of the evolved gas decomposed composition. So TG-29F Libero can be coupled to FTIR, GCMS, and MS. The advantages, I already mentioned some before, is because the low purge gas flow and the small dead gas volumes will be ideal for the good sensitivity for this coupling gas analysis. And like the TG-FTIR measurements at reduced pressure is also possible, which will enhance the separation. Sergey will talk about this example in his second part. So here shows a scheme of the TG-FTIR coupling with the Bruker FTIR instrument. The general idea is just the evolved gas part from top of the TG instrument can directly go through Bruker FTIR. So I will not talk about detail because later also Sergey will talk about detail to explain how the setup is going to work. I just one thing I want to point out in the good job we have for the TG-FTIR, the database. We not only have the good database from the brokers, but NETCH also develop FTIR TG database for polymers, which including 129 spectral at the DTG peaks. So that will provide like a fingerprint identification for polymers by this TTG and FTIR spectrum. Okay, so here is my contact information. If you have questions, you can contact me by either email or phone. So next, I'd like to turn over to Sergey for his second talk on the FTIR with TG.
Thank you for joining us. You now know about how TG works, and basically it shows you a mass change when you decompose sample. But what can you do? Any additional information about this? How the chemistry goes when you decompose sample? Well, let's start with very basic. So you know that all molecules vibrate, and complex vibration of molecules can be decomposed much simpler vibration. This is an example of a water molecule, which is, you can see it can be decomposed to asymmetric situation, symmetric situation, the scissoring vibration. So if you look on typical vibration frequencies, that happens in, it's 10 to the 14, 10 to the 13 hertz. In spectroscopy, we do not use notation in hertz for vibrational frequency. We use so-called wave numbers, which is frequency in hertz divided by speed of light. So if you do calculations, you will see that some molecules vibrate at frequency 4,000 to about 400 wave numbers. So you can ask, how can deal with spectroscopy? Well, we know from physics if dipole moment or molecule change during vibration, so molecule will absorb radiation at a frequency of vibration. So from previous slide, we know molecules vibrate at frequency from 4,000 to 400 wave numbers. So it means when molecule will absorb in this range. So 4,000 to 400 wave numbers, that is related to mid-infrared spectroscopy. This is infrared light. Well, when we're doing spectroscopy, we are not working with single molecules. We work with a sample. So how we do measurements? So we have a sample. We shine infrared light. Part of this light will be absorbed by the sample. And what we measure how much light transmitted for the sample. So basically, we measure transmission spectrum, and based on this, we can calculate how much light is absorbed by the sample. So this is how we link vibration and spectroscopy. The question is, what kind of information we can get from that measurement? So that's, see on that slide, is a transmission spectrum of liquid water through liquid water cell. So that's, you know, the molecule of water is very simple, but that means that the spectrum of these molecules is also simple. Yes, actually, the water molecule shows only two bands. One is band around 3,400 wave numbers. It actually is a band related to symmetric and asymmetric stretching vibration of water molecule. And the big band around 1,600 is related to scissoring vibration of the molecule. Okay, well, that simple molecule gives you simple spectrum. How about more complex molecule? Well, this is an example of hexanal. So more complex molecule, and of course more complex spectrum. So each individual band in this spectrum can be assigned to the specific vibration. For example, band around 1650 wave numbers is related to the carbonyl stretching vibration. Band around 2800 are related to this stretching vibration, CH stretching vibration or CH free vibrations. So basically, each individual band can be related to the specific vibration or to the skeleton vibration of the whole molecules. The idea is, so if you get a spectrum of the molecules, you can easily link it to the chemical structures of the molecule. So each individual chemical compound, shows individual spectrum. So if you have a library of spectra of known compounds, and when you measure unknown compound and run search against library, so you can get spectrum over, you can get knowledge about what compound is this. So this is very fundamental application of infrared spectroscopy. So it's a chemical structure. So when you know the spectrum, you can figure out chemical structure. So that means that you can use this knowledge to identify what's going on during decomposition process. When you decompose your sample using TG, so you can collect spectra, evolved gases, collect spectra, and run through the library search, and you can identify what kind of compounds evolved during thermal destruction of the sample. This is an example of one of the Bruker instruments connected to the NETCH TG, and we have a special model shown on the right side of TIR spectrometer. This model contains detector, contains gas cell. So infrared light from spectrometer goes through the optics, goes to the cell, and then goes to the detector. So that's an example of, that is a slide shows you how it's actually connected. So that we have a FTIR gas cell which is heated, and we also have a heated transfer line from TG to the gas cell. The reason why you need it heated, because if your gas evolves at high temperature, and if a transfer line and cell will be not heated, so the evolved gas will be just settle down on a transfer line and will not go to the cell. So basically, that's to avoid this, you need to be sure that your gas cell and also thermal transfer line is also its elevated temperatures. So we have a special design cell to for that measurements. It's a low volume. It's about 9 milliliters, and the path length about 123 millimeters. So they have one inlet for the incoming gas from the TG and one for outlet valve. We have also thermocouple that we can control temperature through the software. And then we also have a special dual window cell. So that's one window, the front window is make it a KBR, and the second window is zinc selenide. So this particular dual window setup allows to keep temperature constant, homogeneous inside, across the windows and also inside the cell. This is how does it look in much closer. So KBR window, zinc selenide window, and we have a PTFE space between. So in window can be easily exchangeable, and in most cases you don't need to exchange it very often. It's stainless steel cell, so withstand even very, very corrosive gases. Okay, now let's just talk about applications. So how we can really do the measurements, and what kind of examples. First example will be deal with decomposition of aspirin. So when you do decompose aspirin, and that's how does it look, TG curve. So weight loss versus time. So the first, you consider two processes. First process loss, compound lost about 30% weight. On the second stage, it's 60% weight loss. So that's what you can get from TG, that you don't know what's going on behind the scenes. So you don't know what caused these changes and what kind of chemistry goes when you do this decomposition. So if you take derivative of this, and you can figure out first step happens 176 degrees C, the second step 344.6 degrees C. Okay, so it is nice, but what's the chemistry? Now we do FTIR, and then that shows you Gram-Schmidt. So basically overall changes in the sample when you're measuring infrared spectra. So Gram-Schmidt basically gives you exactly the same two peaks, so which is exactly the same, it happens at exactly the same temperature. Well, let's look on the spectra. This is a 3D spectrum of a compound which is evolved from the TG. So obviously, you see there is something process number 1, so there is something evolved at stage number 1, 170, and there is gas evolved in the second stage. So we have a spectra, so then we need to extract spectrum and run against library. So we use library from EPA-NIST library, which contains about 5,000 compounds. So, and we converted this library to Bruker format, so they can, when you collect the spectrum of the gas from evolved from TG, we run against this library and see there is a good match. So first stage means acetic acids come out during this decomposition. Okay, this actually it shows you the spectrum, shows you interface of the search of our software, and you can see then and the red one is a compound come out from the gas cell, and the green one, so the blue one is a library compound, and see that's a very good match with acetic acid. So that's, well, we identify the first stage. So what's going on the second stage? At 345, this is the spectrum we collected, and actually If you run through the library, we can identify that actually is not single compound. It's this spectrum consists of two spectra. One is related to salicylic acid, and the second spectrum is a phenol. So basically, we know what's going on the second stage by running this library. And you also see a peak around 2300 wave numbers. That is related to CO2 peak. So what's based on this knowledge, we can say on the first stage of the decomposition we see salicylic acid evolved, and on the second stage of the decomposition is a phenol, also can be decomposed. Another example, real-life example, is for softener identifications in the polymers. Well, you know that if on the rubbers or